Good. Yeah. Okay. All right. It's my pleasure to introduce the second talk of the afternoon, Nora Szakacs.
Thank you very much, and thank you very much for inviting me here. So what I want to talk about is not geometric group theory per se, but the generalization of it. I'm a semigroup theorist, so I come from a semigroup theory background, and what I've been working on lately is trying to generalize certain ideas from geometric group theory to a class of semigroups called inverse semigroups. And the particular topic that I'm covering today has to do with, is motivated by operator algebras. So yeah, I'll see how much I can cover during my talk.
Just a small comment.
Yeah.
The second talk right today is in this of the first talk, and the third talk is somehow related to random box. But actually, it's nice to have the talk on semigroups. Everybody has seen that in the top of it. It's really essential that you look on semigroups, right?
Sure.
That is not so direct, but connection, I think. So.
Yeah, thank you. Yes. So basically, I'll see how much I'm able to cover during the talk. Normally, when I talk about this topic, I choose to talk about the motivation first. So why I got interested in is how it connects to operator algebras, which results in often not actually getting to the results. So for now, the route I've chosen to take is I will first talk a little bit about about what inverse semigroups are and how you can view them as geometric objects, and then I will talk a little bit about how I arrived at this topic and why this is interesting. So I will begin with an introduction to inverse semigroups. So the definition is very simple. If I have a set S equipped with an associative multiplication, so a semigroup, then I call this semigroup an inverse semigroup. If every element has a unique inverse, which, well, in semigroup theory, we would normally denote it by S inverse, but I'm actually going to denote it by S star. This is a notation that's more common in inverse semigroups coming from operator algebras, which is what this topic fits into, and it also won't confuse you to think that this inverse is a group inverse. So there's this inverse, which is unique, and it has the property that S star S is S, and S star S star is S star. So this generalizes the notion of a group inverse. If you think about operator algebras, if you know what those are, if you don't worry. Yeah, if you have the S as a partial isometry, then the Hermitian adjoint will satisfy this property, which is why inverse semigroups are relevant in operator algebras. So yes, the typical example of inverse semigroups are basically partial one-to-one maps from a set to itself. So if I have any set X, and I take a partial map from X to X, which is one-to-one, so that means that I take some subset of X and I map it injectively to some other subset of X. Then this map has an inverse in this sense, namely just the inverse mapping of this bijection. And then, so if this is F, this is going to be like my F star, then F star F is the same as F, and F star F star is the same as F star. So in particular, sort of this example is canonical in the sense that every inverse semigroup S embeds into oh, I forgot to say, these maps are of course closed under multiplication, because if you multiplication in composition, because if I have another such mapping from here to here bijectively, so G, then basically I can compose the two just on the largest possible domain on which the composition makes sense as partial functions, and the composition will also be a partial one-to-one map. I need to allow the empty map here because it might be that these two don't intersect. So that's also a partial one-to-one. So the set of partial one-to-one maps forms an inverse semigroup with respect to composition, and this star operation, and this is a canonical example in the sense that every semigroup embeds into such a semigroup. So there's an analog of the Cayley representation theorem. So This is called the symmetric inverse semigroup on X. This is denoted by I sub X. Symmetric inverse semigroup. And every inverse semigroup embeds into the symmetric inverse semigroup on itself. And you can actually you can actually this embedding is very similar to how you would do the Cayley representation for groups. So it's by, well, depending on which side you like, it's either by left multiplication or by right multiplication. The only issue is if you look at an inverse semigroup and you look at, say, the left multiplication as a map from the inverse semigroup itself, it will typically not be one-to-one. Inverse semigroups are not cancelative in general. In particular, having a zero element is absolutely allowed. But you also aren't trying to, you're not trying to do full maps. So for any element S, you need to choose a domain, which is a subset of S, on which it will act one-to-one by left or right multiplication, whichever you prefer. So yeah, so you do need to actually restrict the domain.
Is it difficult to define?
Sorry?
Is it difficult to define?
No, I can tell you. I'm not sure if this will come up somewhere in the talk. I'm not sure if I will define it the right way, but basically for an element S, if I want to do it from the left, then I can associate a map lambda S, which maps from S star S to, do I do it the right way? So for S. Yeah, I guess I'm gonna do rho S, sorry, the right maps because that's easier. So yeah, so S star to S, and it's just right multiplication. Yeah. Okay. So yeah, so these are inverse semigroups. Now, what I got interested in is basically trying to view inverse semigroups as geometric objects that are motivated by group theory. So in particular, it would be nice to have a word metric on inverse semigroups. Now, inverse semigroups also have a Cayley graph, right? You can define a graph by saying, well, the set of vertices of my graph are just going to be the set of the elements of the semigroup, and I'm going to have an arrow from S to, so forgive me, I'm going to be working with left Cayley graphs here. I know this is straight for some, but because of the operator algebraic content, motivation will make more sense. So I have an arrow from S to XS labeled by X, if X is a generator. I can certainly do that. Now, the issue with looking at this graph and trying to define a metric on it is, imagine, for instance, my inverse semigroup has a zero, like this one does have a zero, the empty map, so it's perfectly legal. Now, if my X is zero, for instance, then my graph will just look like a star. Everything will be connected to zero by a metric length one. And clearly, you can actually have arbitrarily big inverse semigroup with a zero in it. It completely kills, like geometrically, it completely kills the structure. So trying to just look at the path metric on a Cayley graph is not very useful. Another particular issue is that multiplication is not reversible in inverse semigroups in general. In particular, I don't have, in general, an edge or even a path coming backwards. So, so you could kind of, so one approach would be to define not a symmetric, but a not symmetric metric on an inverse semigroup and try to study that. But that will have the caveat that we don't actually have a metric space. But the important property of inverse semigroups is if I look at the Cayley graph and I look at the strong components, so basically I look at vertices where I can find paths both ways between these two vertices, and these form equivalent classes, and I look at those, and these are the strong components. Then, well, first of all, I have the property that if S and XS are in the same strong component, then I do have that the arrow X star actually goes from XS to S. In general, this is not true. In general, you can have things like this in the field graph. Right? For instance, 0 star is 0. So you can absolutely have things like this. But if I restrict to being in the same strong components, then this doesn't happen. Then within the strong components, I do generally have an undirected underlying graph. So restricting this to the strong components, I can define a distance. Okay, so let's do that. So let me say that so let me fix a generating set. So I fix a generating set. X is generates the inverse semigroup as an inverse semigroup. So this means that any element of S is obtained from X by applying star and multiplication. And I'm going to say that the distance with respect to this X and S and T is going to be, well, I only want to define it on the strong components. So if they are in different strong components, I'm going to define these the distance to be 0. If so what does it mean to be in the same strong component? So S and T are in the same strong components. If I can multiply S on the left to get to T, and I can multiply T on the left to get to S. So that means that S should be in the left ideal ST, and T should be in the left ideal SS. Right? Now this relation is an equivalence relation on the semigroup which has a name that's called the L relation, standing for left ideal. This is equivalent to saying that the left ideal generated by T is the same as the left ideal. Okay, so the strong components will correspond to this L relation. I define the distance to be 0 if they're not L related, i.e. they don't define the same left ideal.
You mean infinity or?
Oh, sorry, infinity, yeah. Sorry, yeah. Infinity, thank you. And otherwise, I'm just going to define the distance to be the distance in the tax metric. Which you know how, I'm not going to write that down. So this is a generalizer or extended metric because my points can take infinite
You
distance.
fix a set of generator? You fix a set of generator?
For this, I fixed a set of generators. Yeah,
Which is X?
Yes.
X. But because X was also space on which X was a.
Yeah, I'm gonna,
yeah,
yes.
Yeah, it's not the same, it's not the same X.
It's not the same X. So this, yes,
Okay.
this is, yeah. I'm going to use X for yet another thing later on. So
Okay.
unfortunately, there's very limited letters in the alphabet and we don't use most of them. So yes. So this is the word metric. Now you might ask, well, this is certainly a metric, but of course what makes geometric group theory work is that the word metric, the metric properties of the word metric relate to algebraic properties of the group. Now here, this is not obvious that it will hold because basically by putting anything in different strong components into infinitely far from each other, it clearly lost a lot of information. Like basically as a metric space, what I did is I had my strong components and I had like directed edges between the strong components and I just forgot about these directed edges. So you might ask, well, okay, but what about these edges? Like, aren't I forgetting too much? It turns out actually, and this is, I think, the two key properties which make word metrics and inverse semigroups meaningful is, first of all, the fact that within the strong components, the distance is symmetric. And secondly, the fact that if I just look at the strong components as abstract edge labeled graphs, then I can reconstruct the directed edges. So the strong components as abstract edge labeled graphs, a set of strong components as abstract edge labeled graphs, uniquely determine the inverse semigroup. So I'm not actually losing information by forgetting about those edges. Okay, so this work metric was basically first abstractly studied independently by. So first, well, what I mean is basically, okay, so first of all, I didn't say this, but I think probably first this word metric is as defined is not unique to the inverse semigroup, right? Because I fixed the generating set. But the same thing holds as for groups. If you change the generating set and your generating set remains finite, then you've only changed the metric up to quasi-isometry. So up to quasi-isometry, I have a unique metric, and the large-scale properties of this metric have been first studied rigorously. So the properties were first studied explicitly, basically independently by Diego Martinez and Fernando in, well, I forget when the paper was published, but I think they were working on this in 2029, 2020-ish. They are both C-star algebraics, so they arrived at this question from a C-star algebraic motivation. I will talk a bit about it later, and independently by Pedro Silva, Bob Gray, and myself, at around the same time, I think 2019. And here we were motivated by trying to do similar things to what Gromov did when he first introduced hyperbolic groups, so trying to find geometric properties which ensure nice algorithmic properties, solvable work problem, and things like that. So that was our work, and this I will talk a little bit more about later. Now, basically,
Are you trying to introduce some generalization of hyperbolic groups for semigroups?
yeah, so we did, yeah, so that was, okay, so in this paper, that was our original motivation. There's a very obvious candidate. Basically, you can just say all of these strong components should be hyperbolic with the same delta.
What are the example of inverse semigroup you want to study? What are the most
I mean, so
the
okay,
starting example that you want to?
so basically for this work, we just wanted to study inverse semigroup given by presentations.
Do you have one example specific that you like more than the other, like the free group for groups, or like...
Yeah, there is a free inverse semigroup, so that can be defined. It's not obvious from the definition that I wrote there, but these do form a variety in the sense of Burkhoff.
There is some maybe nice semigroups, as you say, that are sort of hyperbolically in your definition, but which are not a group, and for which it's not straightforward to them.
So-
some
So
concrete examples.
Okay, so basically the result here is, first of all, you can define a hyperbolic inverse semigroup by just saying an inverse semigroup is hyperbolic if all the strong components are hyperbolic with the same delta.
Yes, you mentioned that. But
Yeah, so the issue with that is, that doesn't ensure a solvable work problem. So there are inverse semigroups which satisfy that property finally presented, which don't have a solvable work problem. So that's kind of not strong enough. What we did here is, if you assume that all these strong components are quasi-isometric to trees, not necessarily by the same constant, then you do have both solvable work problem and you have a language which in some sense is a generalization of the work problem of groups, which is context-free. So that is the result that we have here, basically.
But is there some example that you can write? I don't know, generators and presentation.
Well, I mean, I can write presentations that satisfy, but I'm not sure. So, for instance, if I take the inverse semigroup presentation, I'm not sure if this will be meaningful. I'm sorry. Basically, so you take the group presentation for any surface group of genus at least 2, and you view that same presentation as an inverse semigroup presentation. Then that will, for instance, have these strong components all quasi-symmetric trees. So that will be one, but I don't know if this is the sort of idea that you're looking for.
So if you take for the torus like A, B, A star, B star, A, what is this semigroup? You can explain what is this semigroup because it's complicated.
Well, it's I don't know if there's a good way to explain it. Like you can definitely do this as A, B, A star, B star equals to 1. First of all, this semigroup is not going to be commutative. So it's I can tell you what these what the strong components are. So basically a strong component containing the way you get a strong component containing a word. So you have a word of A stars and A's and B's. Something like this is basically any time what this tells you to do is you start the way you construct a strong component of a word W. What this tells you is any time at every vertex you attach a loop labeled by A, B, A star, B star. So A, B, A star, B star. You do this at every point, and you do Stallings foldings. And the limiting thing will be the strong component containing the vertex labeled by that word. So that means that basically at every, so what will your graphs look like? So you will always have like the full positive cone of.
It's a graph on a tree. There is a tree.
There is a, yes.
There is a tree in A and B, and at every vertex we have this. Is it what you say?
Well, I think you have the full sort of positive cone, and then you choose some. Well, yeah, and then your tree will be sort of embedded somewhere here. Maybe you can have trees because if you have a B here, then that will fold into it. Yeah, so you do have a tree. Yeah, you're right. Yes. So those will be the strong components.
You mentioned that result problem can be.
I mean, here I can solve the word problem, but this is not one that is described by sort of the classes semigroups that we study here. So if you look at so this is genus 1, but if you look at a surface group presentation, the standard surface group presentation of genus at least 2, then the resulting semigroup will be tree-like in the sense that every strong component will be cross-symmetric to the tree. And those have a solvable word problem in general and sort of a convex free word problem in some sense. But if you only assume hyperbolicity, then there's an explicit construction in the paper that it basically goes back to it uses the fact that hyperbolic groups don't have a generalized solvable word problem. So it uses the Rips construction to construct a very explicit inverse semigroup where all these graphs are hyperbolic and the word problem is not solvable.
So you might visualize the problem is.
So basically in hyperbolic, there exist hyperbolic groups where there are subgroups that don't have a decidable membership problem.
Decidable which problem?
Decidable membership problem.
Membership.
So
in the sub, yes. That's for sure.
So that construction gives you a construction of an explicit inverse semigroup that has hyperbolic strong components, but not solvable word problem. So hyperbolicity in that sense in inverse semigroups is too general of a condition. That was what we were originally setting out to do. We were hoping that will give you something nice, but unfortunately it doesn't. Okay. Yes. So anyway, that was the kind of the algorithmic problem that we were trying to, or the kind of semigroup theoretical relation that led us to study large-scale properties of this metric first with Petra Silva and Bob Cray, and independently of that, Diego Martinez and Fernando Nieto studied the same kind of metric, rediscovering it completely independently. So they came from a C-star algebraic background, and in inverse semigroups, like algorithmic questions had been studied even though they weren't explicitly studied through the metric. it was a very natural next step. But from a C algebraic point of view, I think it was much more difficult to stumble across this metric. So what they were trying to do, and this is also the motivation of the work that I'm going to be talking about during this talk, is so they were motivated by a class of C-star algebras called uniform row algebras, which for group theory, there is basically this three-way correspondence between having a group G as an algebraic structure, viewing that G as a metric space, large scale well, I'm going to say like large scale metric space because I only care about the large scale properties. There's an obvious connection here, which is geometric group theory. And there is a third object here, which is a C-star algebra. So I'm going to denote this by C of G. So this is a C-star algebra called the uniform row algebra. So first of all, this C-star algebra can be built directly from the space. So if you have any metric space, you can build a C-star algebra. And secondly, this can also be built algebraically from the group just by using the action of the group on itself. So there is this three-way connection. And this three-way connection turns out to be quite important in recent results of on things like the Forrest-Blomkamp conjecture and the Novikov conjecture. I'm not an expert on either of these things, so what I said about this is pretty much all that I know. So please don't ask questions relating to that in particular. But this turned out to be quite important. And okay, so let's see how much time I have. I maybe want to talk a little bit about these definitions.
You started a few minutes late, so you can go a few minutes.
All right, so okay, so first of all, what is algebra C-star algebra? Maybe not everybody knows. But first of all, you can define the C-star algebra abstractly. It's a complex algebra where you have an operation denoted by star, which is an involution, and you also have a norm with respect to which the algebra is complete, so complete norm. And there's properties in which the three things are tied together, which is what gives the abstract definition of the C-star algebra. However, for the purposes of our talk, all of our C-star algebras will actually be explicitly embedded into the bounded linear operators of the Hilbert space. So if H is a Hilbert space, and BH is just a set of bounded linear operators on that Hilbert space. And first of all, this is a C-star algebra it's clearly a complex algebra. The star is the adjoint, and the norm is the operator norm. And if I take any subset of this, which is closed under the multiplication of the product and the star, and is norm closed as well, then that will be a C-star algebra, and all C-star algebras that come up will explicitly be represented on a Hilbert space like this. And in particular, the Hilbert space that is going to come up for us is, again, forget that I used X before, I'm going to use X again. So if I have X a set, then L2X is the set of square summable complex functions on X. So these are functions from X to C, such that if I sum fx squared, this is finite. Right, so this is a Hilbert space. The norm here is the root of this. So it comes from an inner product. The inner product is just fxgx is pointwise multiplication and summing. And bounded linear operators on this is from a C-star algebra. Now, if you don't like what I said so far, you can just think of bounded linear operators on a Hilbert space as infinite matrices, like infinite dimensional matrices. Of course, X doesn't have to be countable, so you might not be able to actually fit it into a blackboard, even if you write really small, but basically a basis here, Hilbert basis here is just delta x or x to x. It takes 1 on x and 0 everywhere else. So you can just index this matrix by delta x, and a bounded linear operator on L to x is just going to be an infinite matrix, which is sort of indexed by delta x. So you can think of it like that. Okay, so now I will tell you what the, well, I won't really tell you, but I will tell you in a handy way how to do the uniform rule algebra. So if x is a, this worked much better when you use this for some reason. So for again, so x will now be a metric space up to like large scale equivalence, and I will briefly tell you how to construct the uniform rule algebra for a metric space x. Can you see this? Right. So XD is a metric space. So this uniform rule algebra is going to sit inside the bounded linear operators on L to x. So it's going to be an infinite matrix indexed by delta x. And now imagine, and this is where it's a bit handy, like, of course, if I index the matrix by delta x, I have to sort of course, x might not be countable, forget about that for a second, but basically I can sort of imagine that I'm listing all the delta x's here, row by row, and I list them in a way that if x and y are close together in the space, they will be close together in the indexing. Okay, so like I can't actually do this, but imagine I could. In that case, this C-star algebra will be the norm closure of so-called finite propagation operators of finite propagation. And what is a finite propagation operator? Well, in the matrix, you can just imagine that basically all the non-zero values of this matrix are within some delta neighborhood of the diagonal. So it's 0 everywhere else. So I take all such matrices and I look at the norm closure where the norm is the operator norm, and that will be my C-star algebra, CUX, just the uniform rule algebra. Now you can kind of see from this intuition that, first of all, this will only depend on the large scale properties of this metric. And in general, basically you have that it exactly encodes the large scale properties of this metric in the sense that these two C-star algebras, CUX and CUI, are isomorphic if and only if the metric spaces XD and YD are bijectively coarse equivalent. So bijectively coarse equivalent. So bijective, you understand what is coarse equivalent. So if you have, I assume everybody knows what quasi-isometry is. If you take the definition of quasi-isometry, you're basically bounding. It says that you have a map between the two spaces, which were the distance the distances of the images can be bounded by linear functions of the distances of the pre-images. If you drop the assumption that the function has to be linear, and you're allowing any basically any function that is monotonely increasing and goes to infinity and infinity, then you get the definition of being coarse equivalent.
Another name is uniform equivalence, right? Another name for coarse equivalence is uniform equivalence.
Is it? Okay, it might be.
For example, in all papers in Rome, right, it says uniform equivalence, right? But another
Okay.
name for it.
Okay, I did not know that, okay. For quasi-geodesic space, the two notions are equivalent, so coarse equivalence and
Or maybe even fully would be for equivalence. So,
yeah, so, okay, so basically it's just, so coarse embedding from X to Y, is defined
do
that,
that just distance goes to infinity, you know, it's goes to infinity in the space. You know?
you're bounding from both above and below. So dy fx of y should be bounded by some function rho plus dxy from above and some function rho minus dxy from below. And these rho minus and rho plus should both be monotonely increasing and go to infinity at infinity.
Yeah, but since it's usual, right? Ivan or somebody else, right? Ivan, it's the usual definition of uniform embedded, right? Ivan. Yes, sorry.
Yes. This is a coarse embedding, and of course equivalence is again, this that you have to be uniformly close. So the image has to be uniformly close to the space that you're mapping into. And bijectively, well, bijective automatically ensures that. If X and Y are quasi-geodesic spaces, then coarse embedding is the same, the coarse embedding is the same as quasi-symmetric embedding. So between quasi-geodesic spaces, there's no difference.
Because there is a well-known notion of coarse embedding, which is not at all the same as quasi-symmetric embedding. There is this challenge to discuss to describe uniformly equivalent or uniform embedding, like this recent work of Tessera, for example, from Tessera, where for certain invariants like its own properties.
So only between
not only for quasi-symmetric, but for uniform embedding. So
I mean, I'm only claiming that if X and Y are quasi-geodesic spaces,
Yes.
then X and Y are coarse equivalent if and only if they're quasi-symmetric. If you look at grounds,
because there is a well-known definition of coarse equivalence and another name is uniform equivalence, right? And this notion, even for geodesic spaces, for example, for Kelly graphs of groups with the edges like geodesic, right, is very much weaker than just to say by the symmetric.
so if you look at Gorman's original paper where it talks about, I might misremember, but I'm fairly sure this is true, where he talks about large-scale geometry of groups. He actually looks at multiple potential candidates for what large-scale should mean. And he looks at both coarse equivalence and quasi-symmetry, and then he says, oh, but for quasi-geodesic spaces,
He doesn't use coarse, but many other papers like Osin and many other using the
all I'm
coarse
saying is
stuff.
that, okay.
But
Anyway, I'll move on because maybe
there
it's
is
not that
one
important.
course which is not at all to quasi-symmetric equivalence, but you can see some.
Maybe we talk about it after the talk, because I don't think it's that relevant. But anyway, I think this is true. So so that's coarse equivalent. It doesn't really matter. The idea is that basically there's some notion of large scale equivalence.
So maybe the point is that for embeddings, it's very different. For embeddings, this inequality implies that rho plus is linear, but not rho minus in general.
Oh, I see. Okay.
This is what you are.
It might be right.
For,
Yeah, it might be right. That's for embedding is different. Yeah, for equivalence, I think it's not. Okay, so yeah, so where was I? I was talking about the thing that I just did, and I forgot. So let me just. Yeah. So basically, there's this concept of uniform rho algebra, which encapsulates the large scale bijective large scale geometry of space. And I shouldn't have. Oh no, it's right here. Now. An important property here of the rho algebra associated to a group is that it can be also obtained algebraically. So if this comes from, if G is a countable group, and I will tell you how to make a countable group into metric space. Then this is C star UG is basically, well, it can also be obtained as a cross product C star algebra. So L infinity G, reduce cross product G. Now, this construction, I won't go into details, but basically this is, you can sort of think of this as a semi-direct product version of the semi, like as a C-star version of semi-direct products. So L infinity P is a C-star algebra itself. It's sitting inside VLTP as diagonal operator. So these are matrices which are diagonal, and the entries in the diagonal have a finite maximum. That's L infinity P.
Abelian. Abelian one. It's Abelian?
Yes, yeah, it's a good one. And there is a general construction that if G acts in a C-star algebra, what should I know for the C-star algebra? Well, I'm just going to say C-star algebra. Then there's a generic construction of the semi-direct product thing. And in this particular case, that gives you the uniform row algebra. So there is two ways to get the uniform row algebra constructed. Now, the way Diego and Fernando arrived to the metric, to this word metric on inverse semigroups, or finitely generated inverse semigroups, is they were interested. So basically this connection, which is that algebraic construction, G. So that connection is that works for inverse semigroups as well. So there is a generic construction of a cross product C-star algebra even when you have an inverse semigroup S acting on the C-star algebra. And this action, I forgot to say, so this action of G on L infinity P is just a Cayley representation. It comes from the Cayley representation of G. Now, the inverse semigroups also have that representation that I mentioned in the beginning. It's called the Van Manchester representation. So in particular, an inverse semigroup S also acts on L infinity S. So you can construct that cross product C-star algebra algebraically. And then it's a natural question to ask, if you have an inverse semigroup here, you construct this L infinity S cross product S. Can you make S into a metric space such that the triangle completes? That was the question that was asked in this paper, and they answered this for finitely generated inverse semigroups. They said, oh, you have to look at the word metric, which they sort of discovered independently. And what we were trying to do is to try to generalize this for countable inverse semigroups. Now, for countable groups, so G is a countable group. Then there is a unique up-to-course equivalence metric, which is, well, first of all, so I want a metric that somehow relates to the algebraic properties of the group. If you look at the word metric, then it has two important properties. If you look at the word metric coming from the left Cayley graph, it's going to be right invariant under the natural action of the group on itself. That's something that we are keeping, just so that the metric is connected somehow to the algebraic properties of the group. And secondly, we don't want, so if you take if you want to take any countable group, you take the word metric on it with respect to countable generating sets. Then in particular, you can take just the full group as your generating set, and you've killed the metric because everything will be distance one from each other. So that's not something you want. So in order to keep the points far from each other, we are also assuming that balls of finite radius are uniformly bounded. So this is called uniformly bounded geometry. So there's a uniform bound depending only on the radius for every ball of radius R. Of course, for groups, if you bound them with the balls around one from right invariance, you get that all the balls are bounded, but for general metric spaces, these are different. Okay, so I can actually give you a construction of how to do this. If you you take a countable, remember this is a countable generating set. I can list the elements of this generating set, x1, x2, x3, blah, blah, blah. And I'm going to draw the Cayley graph again, but instead of taking just the path metric, I'm going to make edges labeled by x1 of length 1, edges labeled by x2 of length 2, edges labeled by x3 of length 3, and so on. And then I take the path metric. So then I call this, I think I'll refer to this as the weighted. I still have right invariance for the same reason as I do in the Cayley graph, in the path metric and Cayley graph. And this condition is now ensured by the fact that any finite ball will only contain basically a finitely generated subgroup. And it turns out that this construction gives you all such metrics up to course equivalence. So historically, I think the first sort of motivation to consider the countable groups as metric spaces came from topological groups. So I think in the 30s, Burkhoff and Kapitani proved that any second countable Hausdorff group admits a right invariant metric. And I think sometime later, I think Struble observed that it can also be, you can also choose it to be uniformly bounded geometry if the, I think if the space is also first countable, and so that construction existed, and then it was, I think, tradition of, at least this is the earliest reference that I found. If somebody knows an earlier one, let me know. And Smith in 2006, they proved that this is course unique. This is course unique. And the reason you need course instead of quasi-isometric is because you can take two such weighted path metrics where basically for one you label the lengths of the edges are, as I said, 1, 2, 3, blah blah blah, and for the other it's like 1, 4, 9. So it's the squares of the numbers. These two won't be quasi-isometric to one another, but they will be course equivalent. But these are also not quasi-cubic spaces.
Because of the big jumps.
Yeah, yeah. So it's basically the function you need is quadratic in this case to bound one in terms of the other. But for finitely generated groups, course equivalence does not introduce anything more general than the quasi-isometry that we started with. So it doesn't kind of change that part. So this metric is course unique. They were motivated by, they basically wanted to, they were studying the asymptotic dimension of nilpotent groups. And when they were studying it, they wanted to have a meaningful notion of asymptotic dimension for countably generated subgroups. And so in order to have a meaningful notion, you need a unique metric in some sense. And so they proved that this is, that with respect to these properties, the metric is course unique. Okay, so what we set out to do is basically to try that this idea, this weighted path metric, we can do the same thing for inverse semigroups in this industry. You can sort of label label those weights, the generators. You can do the Cayley graph, and you can take the path metric in this labeled Cayley graph. The question is, under what conditions will this metric be course unique? So these are the two conditions that we have for groups. What conditions do you need for inverse semigroups for course uniqueness? So that's what we set out to do. And then we also wanted to study the asymptotic dimension, in particular wanted to, so there's a theorem for groups that says in this triangle, maybe I'll copy the triangle. You have locally finite in the group corner. So locally finite means any finitely generated subgroup is finite. In here you have asymptotic dimension 0. So asymptotic dimension I won't define, but basically it's the large scale. It's a large scale invariant dimension, and it's motivated by the notion of topological dimension, and it was introduced by Gromov.
It is making one moment, I think I was not clear in my question and comments. I wasn't right saying it's equivalence. What I wanted to say, for example, if A embeds coarsely in B and B embeds coarsely in A, there is a question like this. This is very far from saying the same thing on the language of isomorphism. I didn't follow that you need really equivalence, I guess, for your map, right? Just this map from one space to another space. If you write its course in what direction, that more or less will finish, right? If you have something geodesic or quasi-geodesic, it's indeed the quasi-geometry. It's just a comment.
Okay.
I maybe was misleading with my comment, but now I understood.
Okay, all right, yeah. Okay, so these are equivalent to each other. And then there's a bunch of C-star properties which are also equivalent to both of these, which I will list a few. So there's finite, what else was there? Let me check. Yes, finite, stable finite. I won't define any of these, but if you were to say anything to you, you will be happy. Both quasi-diagonal and strongly quasi-diagonal, and locally asymptotically finite, so local AF. So these are all equivalent, and this result was proved by Smith in 2006. So this is the same Smith as here. And these results were, well, basically the equivalence of both of these lists were proved by Scarparo and Lee and Leo in 2018. And I think these implications use the fact that these two are equivalent. Some are easier to prove from the geometric point of view, and some are easier to prove from the algebraic point of view. And this particular result actually enabled Lee and Liao to classify some of the C-star algebras. The C-star algebras basically which arise in this way by supernatural numbers. That was kind of the main goal with that. Okay, so this is basically the theorem that we were trying to generalize for inverse semigroups. And the first step was finding the right notions, which I just erased for groups under which the metric will be course unique. And let me see how much time I have.
I was asking too many questions,
Yeah.
but we are already 10 minutes past the end of the talk.
Okay, all right, okay.
Like 1 minute.
Yes. Okay, so I will. In that case, I will stop here. So this is basically what we're trying to do. So we did basically. I'll just say very quickly. So we did basically find the two equivalent notions, or the two relevant notions for inverse semigroups. Now finding the notions is actually the difficult part. Once you find what are the right notions, then proving the course equivalence is quite straightforward. Now instead of this, we basically have that. I think there's a split into, well, maybe not this, but I think there's a split into two like this. So these conditions split into two. One of them will correspond to local finiteness and asymptotic to the dimension 0. The stronger ones, and the weaker ones will correspond to something which is weaker in semigroups, which is yeah. So we call it locally L finite. So that will correspond to all the strong components being finite, but not within the from bound. Not all in the finitely generated inverse subsegroups. Yes. So okay, and I'll finish here.
Time for one question, if anyone has any questions that were not answered during the talk. All right, and I don't think there is any on the Zoom, so let's go ahead and swap out.